welcome to session 5. In this session we're going to take our primary DNS server and we're going to start looking at how we can start putting in something called rDNS or reverse DNS. We're then going to look at how we put the records in, then we're going to sort of deviate off a little bit and we're going to look at root hints. We've mentioned them a few times, so let's clarify what they are, look at where they come from and how they're managed. Then we're going to have to look at how we build our rDNS. So we need to know rDNS, where it fits into the DNS architecture, but then we need to know how we actually build it for our subnets. So we'll look at how we do that, how we construct the names, and then how we actually implement them. And then what we'll do is we'll finish off with a little general security talk about how rDNS is actually used within the DNS framework to provide us with some security measures. We'll be using in this module, we'll be using it as a means of putting in a security mechanism for shared file sources. It's for shared file storage, but it can also be used for other things such as checking for spam mail, which we'll cover in that section. So what's next? Let's have a look. Okay, so what is rDNS? Well, DNS, as we know it now, takes a name and gives us an IP address. But what happens if we have the IP address and we want to check the name of it? Well, that's what rDNS is for. Now, it sounds quite straightforward, but it actually provides us with a very powerful tool. Basically, what happens is with rDNS and DNS combined together, we can have a URL and then we can check the source of that URL. So it gives us that extra little bit of information. And that is, if we can look at it one way, can we pull it the other way just to do a quick verification? So when connections come into machines, they come in and all we have is an IP address and we can use that because we have rDNS. So it's very good as a diagnostic tool, but nowadays rDNS is predominantly used for security purposes. So the issue we have is we already have DNS, which takes an IP address, starts at the right hand side of that address as the source and works its way backwards. Unfortunately, we have a problem. IP addresses don't work the same way. If we look at the structure, it's very similar. The structure is we have this dot notation, or if IP6 colon, which could be dot notation. However, the issue we have is how do we actually turn an IP address into a structure that can give us a hierarchical query? So that's the issue we've got, and the way that's been resolved is by introducing a new domain name, IN address ARPA. Now we'll come on to that in a moment when we talk about root hints and how URLs are constructed. But for the present, think of rDNS as being the internet address for the ARPA network. Now, if we have a normal domain name, we have this hierarchical structure and it starts right at the top. So we have the dot notation, followed by the .com, followed by example, followed by www. So we tend to write it left to right, but we read it in terms of its hierarchical structure from right to left. So we've got to consider how we're going to map an IP address into here. Well, first of all, what is the highest point of the network? Well, the highest point is the dot. That's the root. That's where root hints come in, and we'll talk about that in a moment. What we have next is we then have what we call the top level domain, or the TLD. So in the case of example.com, dot means root of the internet, com is the top level domain. What we then have is the next level down, which is what we call the second level domain, which is example in this case. And then at the very lowest level, we actually have the host name, www. Now, generally speaking, it's that last part that we tend to have control of, the www. In our case, on our internal network, we're going to take control of all of it. But what we're producing with our DNS infrastructure is something that's called out of band. We'll talk about a little bit more about that when we look at DNS architecture in its full hierarchical implementation. So we need to know how these names are derived, how they're actually managed. And that will give us an idea of where the DNS we're building fits in. When it comes to internet domain names, there has to be some controlling body, and there is an international consortium that does that called ICANN, Internet Corporation for Assigned Names and Numbers. And what they look after is domain names and IP addresses. But we'll look a little bit more at the IP addresses in a moment. But specifically what we're interested in is the fact that they look after domain names. And what they do is they control the top level of the DNS architecture. DNS itself is actually a hierarchical tree. So we have that top level domain, dot, and that is managed completely by the Internet Corporation. The other levels are passed down or delegated, or the responsibility for those additional names is then delegated further down. So let's have a look at how that works. What they do is they manage the very top level of the internet, dot. Then what they do is they have organizations that they then delegate responsibility to, and they basically are what we call registrant or registry operators. They will manage the servers and the domain names and allow them to be entered into the public record. When they're entered into that public record, the IP addresses of the top levels are then registered with ICANN. So there's a cooperative environment there of companies which manage the public names for us. What we have to do is if we want to have any names put into that environment, we have to use a registrant organization. Now, we aren't doing that with our DNS. What we're doing is building what we call an out-of-band DNS architecture to run on the internal part of our company, and then we'll map it to the outside world to get to the root hints. So we're going to manage our own internal queries and our own internal domains, but then we will pass on all of the other querying to this public infrastructure. So there is a slight difference in the way we're running what we're running or building now. So this is for an internal organization and managing its own infrastructure. Now, the way the addresses worked is way back in the 80s, there was only a few. And what they were called, they were sort of global top-level domains, GTLDs. There were only 7 of them. We've got dot, and then below dot, we had com, edu, gov, int, at mil, net, and org. And they actually were specifically designed to be mapped to specific types of organizations. 3 of them were basically for anybody to use, could be used without restrictions. The others were restricted specifically for education, government, military, etc. So there was a very specific structure to how we use them. It's a little bit more lax nowadays, and we can get names within sort of different environments a little bit easier now. But also what's happened is they've been extended. Back then there was only those few, but now there's an awful lot more. Lots more have been released, and even more have been released more recently, things like .me, etc., and various others. If you have a look around, you'll find that there's lots and lots of them. A popular one is .tv for TV stations. That's been out a while now, but again, the domains have been progressing over time, and there's more being released as the internet has got bigger. Now, we do have some little anomalies, and that is, for instance, a lot of us will have seen .co.uk. Now, .co.uk is a top-level domain with UK, but then a second-level domain with co. But I'll talk a little bit later. I'll talk in the next couple of slides about why that's built that way. But for the moment, what we need to consider is this is something that has been building over time. And initially, we only had these 7 top-level domains, and the database for the URLs was not that big. And what happened was, the way it worked was we had, at the very top, we had the initial dot. So this is the root of the internet. Then what happened is we have these global top-level domains. So we had edu, com, etc. And what happened was ICANN delegated responsibility to different organizations to look after whichever of these they wanted. Now, each one can have multiple DNS servers because they can be subdivided. Within those organizations, they could have companies come along and they could register to it. So, for instance, an organization looking after .com could register A, B, C, etc. as different companies associated with .com. However, what happened was, over time, the internet has got bigger, and the number of transactions, as in updates to the infrastructure, has grown immensely to the point that what we have now is not only the global top-level domains, but we also now have country code top-level domains, whereby what's happened is URLs for specific companies have been delegated to the governments of those countries. So ICANN, because of the way it works, being a huge organization that is that is a public company that we all subscribe to use and agree a standard with, they will manage the global top-level domains, delegate them down over, and then they will actually pass on the country codes to each individual country, and they will then manage the country code and anything below it. So, for instance, in the UK, UK.uk is managed by the UK government, and then underneath that we have .co, and we have registrants who can deal or manage that. And then we can have additional host names added below that, or subdomains. Now, UK is a top-level domain, .co is a second-level domain, which is unusual because now everything else is a host name, which are really subdomains, but we treat .co.uk as though the entire thing was a top-level domain. So the way to consider country codes is the country code plus the second-level domain, this is where it gets confusing, is sort of the top-level domain for that country. Now, how is that all managed? Well, all these databases have to be coordinated. Now, that coordination of those centralized databases for the country codes and the global codes is actually the root hints. They are the root hint servers. So when you do a search for dot at the beginning, we have an array of servers that are spread out around the world. The UK component means any of the queries will be transferred to the UK DNS components of the hierarchical database. If anything is a global, like .com, it will go to the global top-level domains to find the servers and where they belong. Now, this list has to be maintained, and the way it's maintained is a branch of ICANN actually manage it. So the internet, so let's have a look, let's bring this up. So what we have is Internet, which is the Internet Network Information Center, which is a part of ICANN. So ICANN is the organization that runs it all, and then within there they have the database of all of the individual IP addresses, and the names and the root hints specifically. So internet.net.zone, this zone here, this company manages the zones, and this database is readily available to the public. So if I now go from here, I can actually go and have a look at that. So zones named.root. So if I go to internet, I can go to /zones/named.root, I think it was, let's check. named.root, yep. And if I go here, there we go. I've pulled back the current version of where all the root hint servers, and I get the IP4 and IP6 addresses. Now, originally there was only an IP4 address for these. As we started rolling out IP6 across the internet, they were added in slowly, and there was an internet version 6.0. Now all of the root hints have both IP4 and IP6. And if we look here at the date, we have 29th of the 4th, 2020. And hopefully you'll recognize the format they're given to their version numbers. 01, first release, 29th of the 4th, 2020. Okay then, so what we have on our servers is we have a root hint. So if we log on to our server, what we'll find is inside etc, there is a file called db.root. And all we have to do is simply take that named.root file and copy it over db.root. And what we've then done is we've then set up the latest version of the root hint servers for our DNS architecture. When we use forwarders in our primary servers and secondary servers, which we'll come on to when we look at secondary servers, what we're actually doing is we are sort of taking away this issue we have of the dynamic aspect of root hints. If we point our server with forwarders to our ISP, what in fact we're doing is saying, we aren't going to run the root hints, we're just going to use your servers. We expect, or we are going to presume, that you will manage that for us. If, however, we want to use the root hints directly ourselves, we can simply stop using forwarders, but now it is our responsibility to make sure that our bind server has the correct root hint servers on it. And what we need to do is, the recommendation from ICANN and Internic is that if we're managing our own root hint servers, we should be actually updating it bi-monthly. That is to capture any changes that take place, which means that either needs done by hand or scripted. Okay, let's get back to the internet addresses and how they work. So we know where the root hints come from, and now we want to know how rDNS can fit into that architecture. We've mentioned briefly and said there are issues with IP addresses and the way they're structured. So let's have a bit of a more detailed look at that. If we look at an IP4 address, generally speaking, the way we've been using it, and if you think about how we've statically addressed our web servers, what we do is we have the IP address and we start from left to right. We have the network address followed by the host. So in this case, for an IP address of 192.168.100.254 and a /24 network, our actual base network address is 192.168.100. And then each host will have an IP address in that range. So a /24 masks the first 3 octets. That's a Class C address. However, what we need to consider is when we look at a URL or a fully qualified domain name, the priority is from right to left. But now our priority is left to right. So we've got a problem. This will not map in the usual way. So what we now need to do is have some alternative way of mapping in the IP addresses and the reverse of them over into the DNS architecture. So what we need to do is we need to create some kind of environment that allows us to delegate responsibility for the IP mappings. And the way we do that is by masking over the top level domain and the second level domain. And the way we do that is by using a special top level domain and second level domain. Top level domain of ARPA, if you want to have a look and do a little bit of research why the name is ARPA, look up ARPANET. And underneath that, IN address, which is your internet address. So by adding those two components, those two domain names, a top level and a second level domain name, what we've done is we're able to add it to the actual root hints. So if we now look at the root hints, we've got our global top level domains, our country codes, and we know how they're cascaded down. But now by having ARPA and IN address, we're able to take those two and cascade those down to now the IP addresses. So we have a way of inserting IP addresses into here. Except the IP address is the wrong way around. We need the network address followed by the host. So what we need to do now is we need to be able to do the mapping. So we need to take the network address, which is the left-hand side, going left to right in priority. And we can do that. Okay, so we can map in IP addresses now because we've added in IN address ARPA. But how do we actually build an rDNS inside bind? Well, we do it by actually formulating a domain name for an rDNS. And the way we do it is shown here. There's ARPA, which is the top level. We then have IN address, which is the second level. And then what we do is, in reverse order, we add in the host name, the network address. So in the case of that address we were looking at, which is a /24, the reverse address will be 192.168.100. We reverse the IP. We then have had added in the ARPA IN address. That allows us to map in the rDNS. Now, when we're using bind, what we would have to do is we will have to do a zone declaration for that. And we simply say we want the zone for the reverse lookup, and it's a type master, and then we say where we want it to be. Now, notice the naming convention follows what we've already discussed for using a domain name with DB at the front. There's one little extra thing I've added in here, which isn't necessary, but I just thought I'd add it in for a discussion point. We're only covering a subset of what we can do with DNS. What we're trying to do is get something that is functional. So there's a lot of things we won't be doing, but I will drop the odd little thing in to discuss it, and here's one of them. One of the options we can put on a zone, and not just the reverse DNS, we can put this on forward as well, is that we can actually say notify no. Whenever we restart our primary server, what it will automatically do is start pushing out updates to our secondary servers. But we may not want to do that. We may be wanting to manage the infrastructure in such a way that we determine when updates are pushed. Therefore, we don't want to restart a DNS and it automatically start communicating with secondaries, because then they've got work to do. We've already planned and done what we wanted to do right at the beginning, because when you build or design your DNS, once you know how it works, you plan a lot more for the deployment. And one of those things would be how the secondaries integrate with the primaries. So in the case of this situation here, what I'm saying is with this zone, don't push updates to the secondary. You will wait for them to be called upon using timing cycles, which we'll come on to later on when we start looking at the SOA record when it comes to secondaries. So it's just to add in another little bit to say there's a lot more we can do. Notify no is one of those things. We've also got notify explicit and notify yes, but we're just going to look at notify no for the moment, and that is if ever I restart the server, don't tell the secondaries that there's you've restarted and there's any updates. Wait for the secondaries to come and get those updates. So just to recap, because we've digressed a little bit there. The zone we declare with the host name of ARPA IN address and then the IP address in reverse for the network segment. It's type master, and then we tell it where the file is, and that file is DB and the host name. So how did I construct that? Well, basically what I did was, having a 24-bit mask, I simply chop the IP address, reverse that first component, and that 254 becomes my host or label. So that is the address that has to go into the actual database of records. So my host name is 254 and my domain name is 100.168.192.inaddress.arpa. And simply take the mask, split the name, reverse the IPs, take the section that isn't part of the actual network, and that becomes the host name. That allows us to do the mapping. As I've said, this is a class C, so the way it works is we flip the base, add the top level and second level domains, and we have our full reverse DNS address. And the host name is the remnant of the IP address when we strip out the network address. So we now know what the address is, we know what the label is, but we now need to get it inside our database. We've created the database, we now need to start mapping in or reverse mapping the IP addresses for the domain names. So the way that's done is using a resource record. We've already looked at A records, etc., and MX records. Well, there's a new record type that we now have called PTR, which is a pointer record. And what the pointer record does, which was standardized in RFC 1035, it allows us to say, here is a name, a domain name. In our case, we've got the domain, and then the actual host name is the last part of the IP address, and we want to map it to a full URL. So how we're going to do that in the database itself? We've got a few things that we've already looked at, things like TTL and origin, and we can use that to our advantage when we build this next rDNS database. The PTR record, the structure of it is the name, and that's the host name. Now we already know for a class C, we split out, for instance, in this case, the 254. We then have our time to live, works exactly the same as A records. If it's blank, it will automatically use TTL, which we can do. We then have the class type, IN for internet. We then have the resource record type, PTR, followed by the name it points to, or the domain name it points to. And this must be a fully qualified domain name, and very importantly, it must include the terminating dot. If you don't include the terminating dot, you will end up with the dot substitution taking place and the origin will be appended and the actual domain name makes no sense. So we must be very careful. Every single one needs its own. Now that may seem like a lot of work, but it isn't, because we should only use PTRs in very specific cases, which we'll come on now. what we've got here is a little table. We can go back to this one, and it's actually in the notes as well. This is reference material as we did before. So 254, it looks like a number, but it's actually part of a URL now. The TTL, we've left it blank. IN is basically, it's an internet record we've got in here. And then we have the actual full name, and don't forget the dot. So how are we going to create that? We know what we need to create, but now we've got to sort of put this all together. And just like we created the forward lookups, the reverse lookups, we create them in a very similar way. We best off using a template, and there's already a template in place. We actually have db.127. Now, if you think about it, localhost has to be defined, and it is. It's actually defined in a record called db.127. And the reason it's called that is because the 127, it's class A. Your local host is a class A address. Wasteful, and there's a lot of discussions about that. Please look that up and have a look at the debate. But we've used an entire class A address just to define a local host. Very strange, very big waste of IP addresses. However, that aside, what we need to do is copy that file and simply copy it to the new file that we want to start building. So in the case of a class C, we've taken the network address 100.168.192.in address ARPA, and we've simply copied it to that new folder. So now I'm taking control of the reverse lookup for this network. Next thing I have to do is edit that file and change the details, because there's already a PTR record in there, but we just need to make some amendments. Now, within this file, what we will only be putting in are PTR records and name server records, but predominantly when we put in the main bulk of records, they will be PTR only. Now, what you need to bear in mind is if you're using class B addresses, the actual reverse domain would actually be cutting off between the 192.168. We'll look at a little example of that in a second. Okay, so we copy the DB file. When we look at it, we'll see that it's set up to a local host, root at local host, and it's basically got the default settings for us. And down here, we have the PTR record for localhost, which is saying it's an internet record, and look, it points to 001. That's because it's pointing to address 127.0.0.1. In fact, it's pointing to 1.0.0.127.inaddress.arpa. So it's the full reverse name it's looking at. So we need to change it. First thing we need to do is we need to put the origin in. The origin allows us to put shorthands in, which makes life much easier for us and reduces errors. What we then have to do is we update. So if I go back and come back, we notice sequence 1, I've put in the date. We go back, we notice I've got localhost and rooted localhost. We've changed that to the names that we want them to be. And then the name server record, we give it the fully qualified domain name for our name server. And in this case, the PTR record, we've actually given it the same name, nsexample.com, because it points to that same machine. So 254 IN PTR record pointing to the name server. Doesn't necessarily need to, just add it in a URL just so for completeness. But that could have pointed to anything. So that could have been gateway, whatever the machine name is. However, what you should make sure is that if you have a PTR record pointing to an address, you should have the forward mapping to it as well. So the two are actually in sync. That said, you shouldn't have that many PTR records in any of these databases. If this was a class B, you'll notice the difference we have now is the origin has the 100 taken off because this is /16 rather than /24. Everything else remains the same, and if you look, except for this label, and if you notice this label here has now got the last 2 octets for the address, but in the sequence of 254.100. So it would be read as 254.100.168.192.inaddress.arpa. Now, as I said, you should use your PTR records sparingly. PTR records allow machines or a device to have both a IP address associated with it and a name, and you can actually follow both a forwards and backwards check. That technique is used predominantly for authentication of machines. So what you don't want to do is add that to every single machine, because what you could end up inadvertently doing is allowing machines to become part of botnets or some other kind of infrastructure that is dependent on rDNS for authentication. So it needs to be done very sparingly. So the only records you would generally find in there would be PTR records for services that are using rDNS authentication. We'll be using that technique when we start looking at file systems later on. And just for information, if you want to look at the importance of PTR records for mail delivery, there's a quick link there for you to have a bit of background reading on. Okay then, let's have a look at why it's important. Well, when we actually send mail records around, very often we get spam. And how do we filter spam out using rDNS? Well, this is sort of bringing in a bit of the security now for us so we can see it in its full implementation. What happens is when a mail message is transferred between mail servers, the actual name of the domain name of the source email is transferred with it. So it's coming from a certain place. What happens is your header in your mail server, this header can be stripped off and checked. So if I'm sending something out over to a certain destination, that's fine. But where did it come from? And there is a alleged source of gmail.com, but that should only come from the gmail.com server. What can be done here is that name that is embedded inside the URL can be extracted, the gmail.com, and we know we can do a lookup on gmail.com for mail servers. The MX record is there. So we can actually take that and say, let's have a look at gmail.com. And we can actually do a forward lookup and say, oh, there's the IP addresses for it. Did it really come from there? Well, what I can do is I have the IP address that this connection came in on. Now, this isn't anything to do with the mail header. This is to do with the TCP connection that comes in. So when you connect to a machine, part of the TCP header has source and destination addresses. So I have the IP address of where this mail message came from. And what I'm able to do is take the URL component, or take the domain name component, sorry, and look up the name and get the IP, and then get the IP that this came in and look up the domain name that it's allegedly come from. And I can compare the two. So I can use the forward lookup I can use the forward lookup on the IP address to actually get the name. Sorry, I can use the forward lookup on the name to get the IP, and then I can use the IP to do the reverse lookup to validate it to make sure that is genuine. And that allows me to actually filter out things like spam mail. What we've done in this session is we've looked at what rDNS is, the purpose of it, what it's there for. And predominantly it's used for security purposes, but its main function is to allow us to take an IP address and resolve it to a name. So now we can do name to address, and we can do address to name. So we've got the full circle of doing it. We also know where the files are located. We know a bit more about how rDNS is actually built into our DNS architecture, and we understand what PTR records are for and how we actually construct them and break them down. So we can create a zone, we can take an IP address and subnet, break it up, identify how we build the actual rDNS domain for it. We can then take the actual host names and sequence that correctly and put those in as PTR records to complete the rDNS. So the next thing to do is now move on and build all of this in the workshop.